It's time. I have a meeting at 12 o'clock, so I will end this class a little bit earlier. Plus, I just finished my first section and everybody looks dead. So maybe we will just do it for 35 minutes or so, and then we can take a break for this week. Okay. Any questions regarding the homework? Okay, just a heads up. I made all the homework to be due the Saturday after the Thanksgiving break. Okay, so if you really want to enjoy your time during the Thanksgiving break, just make sure you do as much as you can before you leave. You don't have to worry about anything to be due during Thanksgiving. And then when you come back, just make sure that you expand your range. Don't just wait until the last day. Otherwise, you will have a lot of things due that Saturday. Okay, so if you could start a little bit earlier. Other than that, I think the homework will be okay. 5.3, the fundamental theorem of calculus. Okay. We talk about Isaac Newton and Leibniz, Gottfried Leibniz. Okay, one of them did it from the left to the right by finding the area under the curve. The other one did it from the right to the left by taking the derivative to find the velocity and accelerations. Okay, magically, these two are the same thing. Okay, and this opens a new era in human wisdom about doing all the physics from the first principle. So that's a very, very exciting formula. Even though it looks easy, for us, maybe we just look at it and say, well, there's some computation, right? But really, there is a lot of things hidden inside, okay, which is really, really powerful. Now, after we finish, last time we talked about, we want several more examples, right? The process. Let's just try to do more. 3 cosine x. Okay. Now you probably start to realize to do a problem like this, you need 2 steps. The first step is you just find the antiderivative. Okay, you can plus a 2 plus a c, doesn't really matter. So we just chose the one without the plus c. And then just keep the ending point and starting point here. Now the second step, once you have found the antiderivative, you just plug in the 2 numbers. Make sure this one first, this one second, and take the minus. The rest is just trying to do the computation. So step 1, find antiderivative, keep the ending points. Step 2, once you find the antiderivative, put the points into the position of the x. You have 2 of them, and the order matters because you're taking the minus. Okay, the top first, the bottom second. We have done this in WebWork. Now you know there's no quotient rule yet. So what we need to do is split them into 3 different terms. And then when I take the antiderivative, it's not difficult. To just do this. Once you have that, the rest is just plug in. Square. And then try your best to simplify. Okay, this is 0. So 9 over 2 minus 6, 4 ln 3 minus 1/2 minus 2 minus 0. 4. There's nothing more you can simplify, so stop here. So step 1, antiderivative. Step 2, everything here, just doing the computation and finish. Sounds good. Try some web work. You will be fine. We would be doing this for the rest of the semester, so eventually you will always, of course, be fine. For now, it's just the notation may be a little bit confusing. So make sure that, I think the only thing that is a little bit confusing is just this one. This is actually a long bar. It stands for nothing. It's just a bar, okay, for you to put the numbers there. So this is not a symbol. All right. Now, finally, the third thing, the accumulation function. This accumulation function is really interesting. It helped us to prove the fundamental theorem of calculus, okay, which is defined by this. Of course, the beautiful property of this one is g prime x equals fx. Okay, what does it do? It take this one, it take a function, it change the right end, at the right end move, the area change, and this one basically tells you the changing rate of the area is exactly the function value here. Okay, that's what this formula means. So with that in mind, let's see some example. Number 1, let hx equals ax, let's just take 2x, okay, sine t dt, find h prime x. Now look at this. This is exactly in the format of gx, right? From a number to x with a function ft dt. Good so far? Then the derivative of this one is just going to be fx, which means just copy the thing in the middle. If this is the area, then the changing rate of the area is the function. Sounds good? All right. Second example, what if hx equals this? What's going on here? Number 1, let gx equal to this. Of course, we know g prime x is sine x, according to what we just did. But this time, what we have here is different. We have x squared instead of x. Sounds good? How do we understand that? Well, let's think about it. What's going on? What's going on is this is 2. This is x. Before, this one was actually moving to the right. As you move, the area change, and the changing rate of your area is going to be the function. Good so far? This time, you change it to be x squared. What's special about x squared? It still moves, but it moves to the right at a different speed, actually at a faster speed than x. Good so far? If your x move by 1, I'm going to move by 1. But if your x move by 2, I am going to move by 4. If you move by 3, I am going to move by 9. So when you are here, I'm here. When you are here, I'm here. When you are here, I am actually here. Sounds good? Should the changing rate also change? The changing rate of the area. Remember, this is the changing rate of the area if you move by x, right? That's fx. But if you move faster, what do you think the changing rate of the area is going to change? It's going to be bigger, because now you simply move faster, right? How much bigger? It really depends on the speed ratio between these two. If you move at 10 miles per hour, I move at 30 miles per hour, I'm going to be 3 times as big as before, right? If you move at 2, now you move at 8, I will be 4 times as fast as before. But how fast does x move? X moves at a speed of 1, and x squared moves at a speed of 2x. Right? So from here, you can see you just simply multiply 2x for the original changing rate. Now you're 2x faster. Okay? How much faster really depends on how far away are you from it. If you're at 3, you're 9 times faster. 6, sorry, if you're 2, you're 4 times as faster. If you're 6, you're 6 times, because each point actually move at a different speed compared to the original one. Okay, so that's the case. Of course, to be careful, this is what we will do. Hx is this. You know, gx is just whatever this one is x. So this one is just nothing but gx squared. Right? Now you're just looking for the derivative of gx squared. Meanwhile, you do know the derivative of gx. Looks familiar? How do you take the derivative? First, you pretend you didn't see x squared. You just think about e to the x. Right? After that, you just times the derivative. That's how you do it. Okay, similar here. You first take the derivative of g, leave the x squared. After that, you times x squared prime. How do we call this thing? This is called chain rule. Okay. Do you know g prime x? Sin x. Now plug in square, and then times 2x. So this is how we do it by chain rule. Sounds good? Your original speed changing rate should be sin x. But now you replace the x to be x squared. So number 1, the original speed is still there. Number 2, you need to times how much faster this time. Okay, my x squared is going to move compared to the original x. That's where we adjust the velocity to be like this. Okay. Now you can forget about everything. Just purely do it by symbols. How do you handle this? Okay. Number 1, write down what will happen if you just replace this by x. Then g prime x, since this is x, you can just replace your t to be x. That is by the definition of accumulation function. Second, your hx is basically gx, but you change the ending point to be cosine x. Right? H prime x is just going to be this one prime. And that is when you apply the chain rule. Sounds good? Anton.
Yeah, so I kind of had a question. I kind of struggle visualizing what this really like means. Do you have like an example off the top of your head?
Let's draw it. Okay, now we know if you move to here, right?
Mm-hmm.
Then your changing rate is going to be cosine. No, your changing rate is going to be square root of x squared plus 1. Good so far?
Mm-hmm.
Now I take this point. What I'm going to do is I'm going to move here, and then I move here, and then I move here, and then I move here. I just keep going back and forth, back and forth, back and forth, back and forth. That's what the cosine x does to me.
Right.
Right? Now what's going on? Your area is going to become bigger, and then your area is going to become smaller, and then your area become bigger, then your area becomes smaller. You're just going back and forth. Still okay?
Yeah.
Okay. So now what's the changing rate? If you factor in this at here, that should be the original changing rate times how fast you are still moving, because you have another layer of cosine. Good so far?
Mm-hmm.
If you just behave yourself, you just move to the right, you will have the original derivative. But now you don't behave yourself. You go to the left. Meanwhile, you go to the left not at the speed of 1. You go to the left at the speed of cosine, whatever that derivative is. So you should take the original velocity times the velocity ratio between x and the new cosine x, which is negative sine x.
Okay.
I'll try to see if I can make an analogy on this.
I know it's putting you on the spot, but yeah. I think that makes sense though.
Yeah, I mean, from mathematics, it makes sense. I'm just trying to say, like, how can I make an example in real life? May not be a perfect example, but you can think about an analogy about, you have a cart moving. Meanwhile, you have a pendulum moving on the cart. Good so far?
Mm-hmm.
The pendulum is going to have the cart is going to have its own speed. That is coming from the original shape of the function. No matter how fast you move, at here, the changing rate of the whole area is just going to be fx, no matter what. Good so far?
Mm-hmm.
But you do have a second component. You can go like this. You can go like this. So no matter how quick, how big this area is, you can still swipe it quickly or you can swipe it slowly. So the speed when you swipe through it also matter. Make sense here? So you have two components deciding how fast is your changing rate. Number one, the original shape of the function. Number two, how fast you scan through it.
Okay.
Good so far? Now what does this one tells you? This one tells you if you scan it at a constant speed as fast as x, you will exactly have fx as your changing rate. Good so far? If you swipe faster than x, you're going to have a bigger changing rate than this. If you swipe slower than x, which is 1/2 x, for example, you can still go through this way, right? You can say, hey, I don't want the right end to move at x. I want it to move at 1/2 x. Then you should not have this speed. You should have half the speed. Still okay? So can you see that? The final thing should be a component of number one, this, and number two, how fast you're scanning through it.
I think so, yeah.
Cool. And we're taking the derivative here. So when I say how fast the cosine x is swiping through something, what I really mean is actually the derivative of cosine x. Okay. Not just cosine x itself, right? Okay. Mm-hmm. Sounds good. So it's almost like the chain rule, right? What do you mean by chain rule? It's basically, okay, if this one changed by 1, this one changed by 2, and if this one changed by 1, this one changed by 3. So if this one changed by 1, this one changed by 6. Right? So if you just think about the last one, basically what you do, you will basically have a changing rate of 3. But if you swipe it as a speed of twice as before, you're going to have a changing rate of 6. So it really depends on the first layer, like how fast you're changing the speed from x to something other than x. Right? So if you have fx, then your changing rate should be f prime x. Now what you did with f2x, what do you mean by f2x? That means you still have the same function. You should have the same changing rate, right? But you swipe it twice as faster. Good so far? Then you should have twice as the speed. And this 2 come from the derivative of 2x. Sounds good? So it's almost like you are speeding up the time interval. Right? You have dy over dt. This is the ratio. If your time changed by this, your y changed by this, right? Okay. But meanwhile, you can actually speed up this dt. And then, of course, your changing rate is going to be even more dramatic. Okay, that's one way to think about it. Another way to think about it is also interesting. What is x to x squared? That's a coordinate transformation. Can you see that? It's basically everything you have x, now it happened at x squared. So if the original graph looked like this, you may have a new coordinate system. The graph look like this now. It's still the same graph, but got stretched. This is x squared. Does that make sense here? Okay, so if the speed is this, now the speed is going to be longer. Why? Because the whole thing got stretched. Still okay? Okay, basically you keep the height, but you stretch horizontally. Moreover, this stretching is not uniform. Here you stretch a little. Here you stretch a lot because it's x squared. If it's x goes to 2x, you basically shrink everything by a uniform factor 2. Okay, so from this point, what you're trying to do is you're trying to take the original speed or the area, but your area got stretched by how much? By the derivative of x squared, by this much. Because originally this was the width of your rectangle. Now this is the width of your rectangle because everything got stretched. You went from x to x squared. Okay, in that way you can also see it got it become faster. All right. Very good question. But if we just look at this computation, does the computation make sense? The process? So basically, if it's anything not x, first make it x. Then you have the derivative, which is nothing but just the inside. That's step 1. Step 2, now plug in whatever you have here, cosine x, into this. Number 3, take the derivative using the chain rule. All right. Well, let's try the last one. Do you see the problem? Okay, number 1, the problem is x squared, which we know how to handle, right? If you're not x, I change you to x. That's fine. Number 2, we have trouble. Why? Before, every time we do this, this one was a constant. Okay, what does constant mean? Constant basically means this. You fix this side, you let this side move. So if you look at the area under the curve, I basically fix my left finger, I let my right finger move. And then I know how to calculate the changing rate if you move at the speed of x. If you move at a different speed of x, I just multiply by the velocity, I can still do the changing rate. Still okay? But this time, what's going on? Both my fingers are moving. The left end and the right end, they're both moving. Good so far? Number 2, they both move. It's almost like a window scanning through the whole function. As the function shape changes, you know the area is going to be different. Therefore, you have a changing rate. But moreover, they don't move at the same speed. My right finger moves faster. My left finger moves slower. Stay okay? So what you really have is you have a window scanning through the whole function to see the area under the curve. So the area is changing. Number 2, the window is getting bigger and bigger and bigger because the right end goes faster and the left end goes smaller. That's what's going on. So you cannot handle it as before exactly. But nonetheless, let's just write down what we have. In order to use the effect, we have to make sure this is a constant. So we just make it a constant. So far, so good. Okay. Now, like we said before, I really want to do gx squared, so I can use the chain rule. The problem is, to use gx, I have to have a. Okay, but I really don't just have a, I have x. That's the problem. Good so far? But can you change this to this? We can simply just add this. Go from x to x squared is the same as go from x to a, and then a to x squared. That's the property of the integral. Certainly doable. Then the first part, we do have this. The bad thing is we have a leftover. Can we handle the leftover? What's this? I really wish the x is here and the constant is here. Then I can use whatever gx I have done to do it, right? Can you change this to that? What happens if you take the integral and you switch the starting and ending point? We just take a negative. I switched. Plus become minus. Once I switch that, I find this is nothing but gx. All the area up to my right finger minus all the area up to my left finger. Both are moving. Good. Both have a velocity. So how fast is it changing? The first velocity minus the second velocity. That will be how fast it's changing. G prime x squared minus G prime x. Again, because we assign G prime x to be this, it's going to be e to the x squared times 2x minus e to the x. Sounds good? This is what we just have done. Okay, look at my fingers. I'm going to stop this so we can have a bigger screen, hopefully. How do I make sure you only see my face? Can you guys see me? See my finger? Okay. The first thing we do is we have a area under the curve. We fix one side. We move the other side. Moreover, we move the other side at a speed of 1, which is x. In this way, we know how to calculate the derivative. The derivative is basically what's inside the integral. Good so far? Second case, I still fix this side, but this one now can move in random speed. It can move faster than x. It can move slower than x. It can move back and forth in x. Whatever. Okay? And the way to do it is use the chain rule. Number one, I consider how high the function is here right now. Number two, I consider how fast my finger is moving compared to the original x. Still okay? Number three, what's going on? Both fingers are moving. They can move at different speed. I'm trying to look for the area under the curve. Still okay? What are we going to do? What we are going to do is we're going to take a benchmark which is other than my finger. We're going to fix a third point. Good so far? Then what we do is we take this point of my right finger. I can do whatever I just did previously because one side is fixed. Then I take this point and calculate the area between this one and my left finger. That's another area. Again, I keep one side fixed, the same point fixed. Still okay? Then what's going on with my two fingers? If you can visualize the third benchmark here, basically it's just like this minus that. I will see what's going on in between. So I do the same thing for twice. Sounds good? That's the idea. the computation, of course, you follow exactly what we write down. It's going to be a chain rule. Okay, but what the chain rule does is nothing but, take the original x derivative, x speed, and then modify it by the new speed. Okay, that's what the chain rule does. Is everything clear? Okay, if that is clear, that will be all for today. Tomorrow we start, Monday, we will start 5.4. Okay.